At this point, we already know the different methods of solving first order and first degree ordinary differential equations. So we now go to the different applications of the said differential equations. So there are many applications, geometric and physical applications, but in this video, we're going to focus on the geometric applications of first order, first degree ODEs. There are many geometric problems that can be solved here. We're going to focus on these, the equations of different curves and isogonal and orthogonal trajectories. And in solving problems like this, we have to recall our knowledge in distance and finding the distance between 2 points. Remember the distance formula. Distance from a point to a line. If you're given a point and given the equation of a certain line, so how do we find the distance from a point from that point to the given line? And we have to recall um, if the distance if the distance is positive or negative based on the location of the point, if it's above the line or below the line. It's also important for us to recall how to find the angle between two curves, determining the slope of a normal and a tangent to a line. Recall the tangent is the first derivative of a certain curve at a specific point of tangency xy, and the normal has a slope which is the negative reciprocal of the slope of the tangent. We also need to recall the different standard forms of lines, especially the point slope form of a line, and of course, identifying the different types of curves and their equations as well. So for example, we are to solve the given problem. We are to find the equation of family of curves or a family of curves in rectangular coordinates has a slope negative 2x over y at any of its point xy. So we are to find the equation of the family. Also, we are to find a particular member of the family which passes through the point 2, 4. So we're looking for two here. First, the equation of the family and a particular member of the family passing through 2, 4. So just like in any problems that we need to solve, we have to know what is given, what is being asked. So we already know what is being asked here. And um, of course, solve it to get the answer. So first, we are given here that the slope at any of its point xy is negative 2x over y. So we recall the slope is equal to the derivative dy dx. So the slope at xy is equal to negative 2x over y. So dy dx is equal to negative 2x over y. And this is actually our differential equation already. So solving the dE, this can now be solved by separating. So y dy equals negative 2x dx. So 2x dx plus y dy equals 0. So we now integrate to find the family. That's x squared plus 1 half y squared equals c sub 1. And multiplying both sides of the equation by 2, we get 2x squared plus y squared equals c, where c is equal to twice of c sub 1. So that is now our general solution. That's the equation of the family. So as we can see, it is a family of, what is it? It's a family of parabolas. So if we're going to reduce it to its standard form for a parabola, we divide both sides of the equation by c so that the right side will be equal to 1, we are going to, we'll be able to reduce that to x squared over c. We divide both sides of the equation by 2c. So x squared over c plus y squared over 2c equals 1. So as you can see, the denominator of y squared here is greater, telling us that the ellipse, okay, it is an ellipse. The center is at the origin, and that the major axis, or the major axis rather, it's a family of ellipses, centers of the origin, and their major axes are vertical. So to find the particular member of the family passing through 2, 4, okay, for the particular member, we simply substitute 2, 4 to solve for c. So c is equal to 2x squared plus y squared. So passing through 2, 4, c is equal to 2 times 2 squared plus 4 squared. So that's 8 times 4 times 2 is 8 plus 16. That gives us 24. So our particular solution is 2x squared plus y squared equals 24. So that's our particular member of the family. And if we reduce that particular member of the family to its standard form, we divide both sides of the equation by 24. That's x squared over 12 plus y squared over 24 equals 1. So the value of a squared here is square root of 24. That's 2 square root of 6. And the value of b squared, a here is square root of 24 and b here is square root of 12. So if we are to draw the members of the family of ellipses with centers at the origin, so they would be looking like this. Because their centers are at the origin. Remember, it's an ellipse, not a circle. And say, for example, this is our particular member. So if this is our particular member, if that is our ellipse, okay, our A is square root of 24, it would be this distance. And our B, square root of 12, would be this distance right here. Okay, so those are the family of ellipses. Slope is negative 2x over y at the point xy. You have to learn how to draw your family of curves. Okay, you have to recall your lessons in analytic geometry. Okay, another problem. Find the equation of the curve such that the tangent at any of its point xy intersects the x-axis at a distance from the origin equal to the abscissa of the point. Again, find the equation of the curve such that the tangent at any of its point xy intersects the x-axis at a distance from the origin equal to the abscissa of the point. So for us to have a better picture of how this curve or how this point looks like and that the position of this tangent line, let us assume this is y-axis, this is x-axis. let us assume that our point on the on the curve xy is this yellow. So remember that the x and y here, abscissa and ordinate, are the horizontal and vertical distance of a point from the x and the y axis. So if you have an abscissa x, that's actually the horizontal distance of the point P from the y-axis. So this is our x right here. And this y-ordinate is the vertical distance of the point from the x-axis. This is y right here. This distance is y. This distance is y. This horizontal distance is x. But then the problem says that the tangent at any of its point xy, meaning there is a line passing through this point, maybe inclined to the right or inclined to the left, such that, so let's assume that this is inclined to the right. At any of its point xy intersects the x-axis, okay? If this distance is x, the distance of the x-intercept of the x-axis from the origin is also equal to x. So it would be impossible if the x-intercept of the line would be here, because that would be greater than x. It means that it must be here on the other side. So for example, the point, the x-intercept is at this point here. That's the x-intercept right there, meaning the tangent line will pass through the point xy and will touch also this point here on the x-axis. It's x-intercept. So this would be the position of our tangent line. Okay, this is our tangent. And it says again that the distance from the x-intercept, okay, intersects the x-axis at a distance from the origin. So remember, this is our origin right here. Its distance from the origin is equal to the abscissa of the point. And what's the abscissa of the point? It's x. X is the abscissa. So meaning this distance right here is also x. So this total distance right here is 2x. And this vertical distance right here is y, which already gives us the slope of the tangent line. So from the drawing, the slope dy dx is equal to y over 2x. And that is already our um that's already our differential equation. So dy over y equals dx over 2x. So dx over 2x minus dy over y equals 0. Integrating, that would give us 1/2 ln of x minus ln of y equals c sub 1. Multiplying both sides of the equation by 2, that's ln x minus 2 ln of y equals twice of c sub 1. If we let c sub 2 be equal to twice of c sub 1, then this would now be ln of x, simplifying ln of x minus ln of y squared equals c sub 2. So by applying laws of logarithm, ln of x over y squared equals c sub 2. So e to the power of ln of x over y squared equals e to the power of c sub 2. So the right side of the equation would become x over y squared, and the right side of the equation would now be equal to c, wherein c is equal to e raised to the power of c sub 2. And so x is equal to cy squared. So this is the equation of the curve whose tangent at any of its point xy intersects the x-axis at a distance from the origin equal to the abscissa of the point. So x equals cy squared, or what is this curve? These are actually family of parabolas. So y squared equals cx, that would be a family of parabolas, either, okay, that would be facing right or left. Okay, so that is our general solution to the problem.